The cell phone charger is a typical example of isolated power converter. So like in cell phone chargers, we typically have a flyback converter inside it. So next, we are going to utilize the flyback converter example to show you how to build the DC steady-state model of the isolated DC-DC converter. So first, let's see how can we derive the flyback topology. So the derivation of flyback indeed, the flyback converter originates from the buck boost topology. So first, we plot a inverting buck boost topology. So here is the input source, and here is the MOSFET Q, and here is the inductor L, and here is power diode, filtering cap, and load resistor. So this is the output voltage. So based on the inverting buck boost topology, we can first do a little bit modification to the inductor here. So we can introduce a transformer with 1-to-1 turns ratio. Inductor winding by introducing 2 wires. And replace the inductor by 1-to-1 turns ratio transformer. So now let's see what happens graphically in the schematic. So input source. Q. Replace L by a 1-to-1 transformer. And we add 2 wires to short primary and secondary winding. The rest part are the same, unchanged. D. So L. If you compare the electrical behavior of this circuit and this circuit, you will see that those 2 circuits, they are equivalent, which means that the basic functions are unchanged. Then we can go further. So since those 2 wires, here and here, if you analyze or simulate this circuit, you will see that there is no current flowing through those 2 wires. So it means that we can just open it. By opening those 2 wires, the total current are unchanged. And the current will distribute differentially. the current will be distributed differently. Okay, so now let's plot the modified circuit schematic. So this is one-to-one transformer D R C R output voltage. So this topology is very close to the flyback converter we're using. And next, we are going to formally introduce the flyback topology, which is quite similar to this one. First, let me plot the schematic of a flyback. So input source, transformer, MOSFET, Q, and diode, load network with C, D, R. So here is the output voltage. And the turns ratio for this transformer is 1:n. And there is a Lm on the primary side of the transformer winding. So you will see that this, we call this as the flyback transformer. So for flyback transformer, the current does not flow simultaneously. In both winding. So if you compare the flyback topology with this modified buck boost topology, you will see that there are several differences. Right? So now let's summarize those differences. So for this usual configuration of flyback, so first the change is the MOSFET, right? Originally, MOSFET is on top of the primary winding, but in the usual configuration, we have the MOSFET source connected to the primary side ground. So MOSFET source terminal grounded on the primary side. This brings us practical benefits when we design the drivers. So it makes driver circuit design much simplified. And secondly, if you compare, right, the polarity of the coupling point on the secondary side are reverted. So the transformer coupling point polarity is reversed. On the secondary side. This is mainly because we want to have a non-inverting output on the load side. So we just easily can reverse the polarity of the coupling to achieve this target. And thirdly, we introduced the 1-to-n turns ratio. Here is like 1-to-1, right? Here we can modify to 1-to-n. This gives us lots of benefits for better converter optimization. You can easily utilize the transformer turns ratio to step down the voltage or step up the voltage, depending on different kind of applications you will implement. Okay, now let's erase the whiteboard. Okay, we have erased the blackboard. Now let's try to analyze the flyback converter. So the first step is that we, as we mentioned, that we replace the transformer symbol by its equivalent circuit model. So by introducing a magnetizing inductance on the primary side, so the rest part will be the ideal transformer. So this is a 1-to-n ideal transformer. Diode, MOSFET, load. So the circled part is the transformer model we have previously learned. So then we analyze the operation modes for this flyback converter. Basically, there are also two operation modes. So for the operation mode 1, we will have the MOSFET on, diode off. We can plot its equivalent circuit. LM. So Q is on. We replace Q by a short circuit. Diode is off. We replace it by an open circuit. So for this equivalent circuit, we can define the several quantities like the input current, Ig, and magnetizing inductor current, Im, and also the voltage across it, VL. And here is the capacitor current. Here is the coupling point, the input voltage. Based on this equivalent circuit, we can express the expression for VL equals to the input voltage. And the small ripple approximation tells us that this is equals to the DC component, capital VG. And the other one is capacitor current. So this current based on KCL is equals to minus the load current. Small ripple approximation tells us that this is minus output voltage over R. Third one is the input port current equals to, since the secondary side is opened, so there is no current flowing in these parts, so Ig will be equals to the Im. And we also adopt small ripple approximation. This equals to I, which is the average value for inductor current. And correspondingly, we can plot the waveforms in time domain. So this is inductor voltage in time domain. From 0 to dTs, the VL equals to input voltage. And the IC, so IC is a negative quantity, so equals to minus V over R. Third one is input port current. Which is a positive quantity. This is input current. Okay, next let's look at what happens in mode 2. In mode 2, the MOSFET is off and the diode is conducting. So we can plot the equivalent circuit accordingly. So here is open circuit. The diode is shorted. One to N. So for this circuit, we can also mark those quantities, Ig, Im, and here is IC. Here is the voltage VL. So we can write those three equations correspondingly. First, the inductor voltage. So the primary side winding is primary side switch is open. Secondary side voltage equals to minus V. So coupling to the primary side, since this ratio is 1 to n, so we'll have this voltage to be equal to minus output voltage over turns ratio. This is applying the small ripple approximation. Second one is IC. So IC equals to the subtraction of this current and this current. So equals to I over N, which is the primary side of the current coupled to the secondary side, right? Minus the load current, V over R. Small ripple approximation, right? This is capital I over N minus capital V over R. Third one is the input port current. Since the MOSFET is turned off, so the IG just equals to 0. And correspondingly, we can make up those three waveforms accordingly. So from DTS to TS. So this is minus V over N. And IC equals to this quantity. It is a positive number. So value here is I over N minus V over R. Current, input current equals to 0. That's the complete waveforms after we adopt the small ripple approximation. Then we can deal with those three waveforms. So first, we apply the volt second balance. To the LM. So volt second balance means that at steady state, the average inductor voltage equals to 0. And based on this profile, we can see that average value equals to proportion of mode 1 times level of mode 1 minus d prime times V over N equals to 0. So we can derive the conversion ratio. Accordingly, MD equals to the ratio between output voltage and input voltage equals to N times D over D prime. This is interesting, right? If you can see, this part is exactly the voltage conversion ratio for non-inverting buck boost converter. So the Flyback has its voltage gain equals to N times non-inverting buck boost converter voltage gain. The N is the step up effect of the transformer. And then next is the charge balance. Charge balance principle means that the average capacitor current at steady state equals to 0. This can be easily found by this waveform profile, right? So D times level 1 plus D prime times level 2 equals to 0. And based on this, we can find out the DC component of the magnetizing current, which is the capital I, right? So capital I equals to N times V over D prime R. And last one, we can also find out the DC component of input current. So which can be found by the average of Ig, right? Mode 1, the level is I. Mode 2 is 0. So the average Ig equals to D times I. So equals to NVD over D prime R. Till now, we have fully analyzed the DC features of the flyback converter. Okay, so in this section, based on the flyback topology, we demonstrated how to utilize the transformer equivalent model to analyze the DC-DC converter. As we can see, after we introducing the equivalent circuit of the transformer, we can use the similar principles we learned before when we studied the non-isolated DC converter to analyze the operation of isolated DC-DC converter.